Okay, let's continue. So, in the last class, we saw how to make a comparator. We essentially started off with a simple common source structure like this. We wanted to turn it on or off, so we decided to add a switch. And for the other differential input, we added the second transistor. But then, initially started with having a simple resistive load at the drain. But then we saw in the presence of parasitic capacitors, the comparison time is going to be quite long. So we decided to use a negative resistance, and we kind of emulated a negative resistor using a cross-coupled PMOS transistor like this. And then we did this first. But then later we saw for small differential inputs, even after the comparison is done, we still had a direct path from VDD to ground that resulted in static power dissipation. So to get rid of that, we decided to introduce an NMOS transistor, which is also cross-coupled like this, right? And also before start of every comparison, we decided to reset all these nodes to VDD so that we start fresh without any memory of the previous result. And the structure is called the strong arm latch, and it's one of the most commonly used architectures. Cool. So now we know how to make a comparator. We already saw how to sample the signal, do everything. So it's time to put all the pieces together and start making ADCs. That's what we'll do. And we'll start with a simplistic implementation. Let's say we want to make a 2-bit ADC. And let's say I have a single-ended input Vi, and say it can span anywhere from 0 to VDD. So let me mark it like this. This is the range my input signal can span, and I want to quantize it to 2 bits. So how many levels I should quantize the input signal to? 4 levels. So I'll basically have these as the reference voltages. So this is VDD by 4, 2 VDD by 4, and 3 VDD by 4. Okay. So I should compare my input with how many reference voltages? Let's say I have the input, I want to quantize it to 4 levels. So how many reference voltages with which I should compare my input to? 2 or 3 or 4? I want to take, in English tell me, right? I want to quantize to 4 levels. With how many reference voltages I should compare my input so that I can get this 4 levels of information? 0.9. I should compare with this, right? Only if I compare with these 3, I can find out in this where my input lies. Fine. So how many comparators I need? 3 comparators. So again, I'll just directly show. This is how it's going to look like. You feed the same input to 3 comparators. This is a brute force implementation. You feed in the 3 reference voltages, and you do. And how do you think we can generate these voltages from VDD? We can use a resistive divider. So that gives you something like this. So if all the resistors are of equal values, so this fellow is what? What will be this voltage? This is VDD by 4. This is 2, I'll just say 2/4 and 3/4. Okay. Fine. Great. So now you see, if I compare the input with 3 reference voltages, I get 3 outputs from the 3 comparators. But I wanted to quantize this fellow to 2 bits. Okay. So let's see what's actually happening here. So let me copy paste this also. So now tell me, if let us say my input is lying in this range, it is smaller than all the 3 reference voltages. So what will be the output of the 3 comparators? 3, I should have 3, right? What will be this, what will be this, what will be this?
0, 0, 0.
All are 0. Okay. Now let us say it is lying in this range, which means it is greater than the first reference voltage, smaller than the other two. What will be in this sequence? 0, 0, 1. So similarly, if it is lying in this range,
0, 1.
fine. And finally, if it's lying in the last range, it is greater than all the reference, so it's going to be. So ideally, we wanted a 2-bit binary data, which is, let's say, 0, 0, 0, 1, 1, 0, 1, 1, which is basically in decimals, it's 0, 1, 2, and 3. This is how you would like to quantize it too, but you see that we are getting 3 bits here, and this kind of coding is called thermometer coding, because if you see, it looks like, I don't know if you guys have seen old thermometers using mercury. So it looks like the mercury level is kind of rising, so they decided to call it thermometer code. So for a 2-bit data, we have 3 comparators, so we have 3 thermometer codes. I have to convert this finally to a 2-bit binary data, and you see here, if the output is 0, I have all zeros. If it should be 1, I have 1 here. If it's 2, I have 2 ones. 3, I have 3 ones. So what is the simplest way to convert this 3-bit thermometer code to a binary code? If I have 0, I have all zeros. If it is supposed to be 1, I have 1 and other 2s are zeros. If it is 2, I have 2 ones, this is 0. If it is 3, I have 3 ones. So what is the simplest logic? What is a decoder? I mean, in English, what will you do? Decoder, I have no idea what a decoder is. In English, tell me first, right? I just have to count the number of ones here. It's as simple as it. If I have 1 1, it is 1. 2 ones, it is 2. 3 ones, it is 3. How do you count the number of ones? I have, digital data, 0 or 1. I have to count the number of ones. What is the simplest block that can do that? Adder. I mean, you just take up all the bits, add it, it's going to give you the number of ones, and that's what we do in practice. So you take all these, give it to an adder, and you get the final 2-bit data. Fine. So this is basically 2 bits. So in general, if I have an n-bit ADC, if I were to extend this logic, how many comparators I will need? For 2 bits, it's 3. For n bits, okay. Is it fine? So which means at the output, I have 2 power n minus 1 bits of thermometer code. Okay. To convert this to an n-bit binary, I simply have to take all these 2 power n minus 1 bits and then add it. Okay.
How does the adder look like?
This adder, I mean, you might have learned in digital electronics, you can use any kind of adder you want. It's a digital adder, right? So there are multiple ways. So I'll come to that. I mean, we'll not discuss in detail. I'll leave it as something you can figure out. And this kind of structure is called the flash ADC. Because essentially it samples the input in one shot, compares the input with all reference voltages and gives the data instantly. So in a flash it gives the data, so that's why it's called flash. Yeah, and since flash is supposed to be the fastest ADC because it is just doing in one shot, you try to use the fastest adder you have, right? There are different topologies. I am not going there. You can take classic digital electronics textbook, see whichever is the best one, just use it. Cool. So this is for a single-ended case, but in practice we already know we have differential signals. So what we will have is, let's say I have
So then, actual practice, which type of adders do they use? Like, they use ripple carry adders?
No, ripple carry adder is one of the slowest, right?
Yes.
So you kind of use, I mean, there are multiple, there are Wallace tree encoders, you can use carry look add, I mean, anything. Wallace tree adder is one of the most commonly used. Cool. Yeah, so let's see how we can do differentially. So right now I'll have two inputs, Vi plus and Vi minus. Okay. So remember, we'll feed the inputs as VCM plus the differential input by 2, VCM minus the differential input by 2. That's how we'll feed it. And just to remind you, VCM is typically half the supply. Okay. So if so, can you tell me what is the range of voltages VID by 2 can take? The minimum I have is 0, maximum I have is VDD. Okay. No, can you see? I mean, so which means the minimum it can go 0, maximum is VDD. What is the range this can take? Minus VDD by 2, 2 plus VDD by 2. Clear? VCM is VDD by 2, so which means my differential signal can span this range. So the goal for me is to take this differential signal, which can span this range of minus VDD to plus VDD. Take some more space. So this is minus VDD to plus VDD. This is the range my differential input can take. I have to quantize this range to so many levels. If you have n bit, 2 power n levels, so you will compare it with so many reference voltages. So I'll just randomly draw. These are the reference voltages with which you are going to compare your differential signal. So let us say this is the kth reference voltage in the differential way. No, in the sense, I mean, here for a 2-bit case you have to compare with 3 voltages, right? These are the reference voltages. Similarly, for n bits you will have so many reference voltages with which you have to compare your input. And again, this is a differential input, so the reference voltage will also be differential. But in practice, again you have to feed it as reference plus and reference minus, right? If I add a differential input VID, the positive input was fed like this, negative input was fed like this. Similarly, if I have a differential reference VRDK, how will I feed it as positive and negative? I mean, if it is VID, I was feeding the positive as VCM plus VID by 2, negative as VCM minus VID by 2. Now I have a differential reference voltage, let us say VRDK. That's basically VCM plus VRD, the kth reference voltage by 2. Similarly, this is minus the differential reference for the kth level by 2. Okay. This is how you'll have to feed it. Okay, simply because we don't have negative voltages, right? It is all 0 and VDD. If you take the difference, yeah, it looks like it is negative. So, which means first we have to generate these voltages, and we'll start from a simple case. We'll first see how we can generate this differential reference voltage. So I have VDD and plus VDD and minus VDD, let us say. How can I generate all these reference voltages, equally spaced reference voltages? The same resistive divider I will use. Again, you put so many of them. So let us say this is the first differential reference voltage, and it goes up like this. Fine. So now we have found a way to generate this voltage, but what do I want? I want this voltage by 2. What is the simple change I can make here so that all the voltages I tap here are scaled by a factor of 2? Yeah, I mean it's a linear network. I scale the inputs by 2, everything scales by 2. Fine. So that's what we'll do. We'll divide it by 2. This also divides by 2. So this is nice, I have gotten this. Now what I have to do to this? I should add another VDD by 2. So let me actually copy this. Yeah. So as of now, this is powered from plus VDD by 2 and minus VDD by 2. So you get this voltage. Now I want to boost all the voltages by VCM. What is the simplest thing you can do?
Add VDD by 2 to both the rails.
Yeah, I mean, basically this is your reference. If you add plus VDD by 2 here, so everything kind of boosts. Fine. I am shifting all the voltages by VDD by 2. That's all. It's a linear circuit, so whatever you do linearly scales. So if I add VDD by 2 here, this becomes 0. And this becomes VDD. So you are set. And this you get basically plus VCM. Okay. So this is how you can generate the positive. Same thing you can do for the negative. So I already have this fellow. Let me actually copy this.
Won't VCM be reduced by a factor?
Why? Why so?
I mean, like suppose you have say n resistors,
Mm-hmm.
so like it would be VCM by Rn times R.
No. What I have done, I have added VDD by 2 everywhere. If I add this both VDD by 2, everything shifts, right? It is as though you are taking the ground, boosting the ground. Ground is the reference voltage 0. If you shift the ground by some voltage, all the voltages in your circuit same, right? So okay, so let me actually make some more space. Yeah. So we just have to generate the negative references. So here I am getting plus VRD by 2, but I want minus VRD by 2. What change I will make here?
Minus VC.
No, this is the circuit.
Whatever S1 has to be plus VDD by 2 and
This is the circuit. The inputs are plus VDD by 2 minus VDD by 2. The input is some plus V. I want the output is some plus V. I want the output to change sign, which means I will flip the signs of the input. Okay. Again, we just keep exploiting linearity. This becomes plus. Okay. So, which means this will become minus VRD by 2. Again, I have to add VCM to this. So, I'll keep boosting everything by VCM. So, this becomes 0. This becomes VDD. So, VCM is added here. So, which means maybe I should go to next page. Let me take this. I'll just draw this here separately. Yeah, this is generating the positive references. And if I redraw this, this is 0. This is VDD. This is generating the negative references. So again, I can basically flip it and then draw it like this. I will say this is VDD, or let me draw it separately. So the same thing I'll flip and draw like this. I'll say this is 0 and this is VDD, and the point closest to VDD is the first reference voltage in the negative side. So this will be that voltage. Again, this should make logical sense, because if I look at the reference voltages here, now let us say in this range of plus VDD and minus VDD, what is the middle voltage, do you think? 0 is the middle reference. If the differential reference is 0, what is the positive and negative references? If this guy is 0, both of them are at VCM, which is VDD by 2. If I were to get VDD by 2 in this resistive ladder, where will I tap? Exactly at the middle. So if I tap at the middle, let's say this is the middle, I get 0. Now if I want to go up, I'll go up here and down here. Similarly, right? So that's why it's kind of symmetric. So the bottom one here is the the bottom one here is the first positive reference. Top one here is the first negative reference, and so on. It just keeps coming like this. Cool. So now we know how to make this, generate this reference voltages. Next is we have to see how we are going to do the comparison. In a single-ended case, it's trivial. We just had one input. We had one reference voltage. You just go and feed it to the comparator. All is set. But right now, what I have is a differential case. I have Vi plus, Vi minus. Similarly, I have the reference as plus and minus. Okay. So what we should be doing is the following. So I'll compare with Vi minus minus Vr minus. Okay. I mean, if it was single-ended, you are just doing, you are comparing Vi with the reference voltage. Now it's a differential, so you have to do this and compare this. So which means to one input of the comparator, I should feed this. Other input, I'll be feeding this. That's the way we should operate. So now let us say I have Vi plus here. To the comparator input, what should be the voltage I should be feeding? Vi plus minus Vr plus. So if this is Vi plus, how can I get Vi plus minus Vr plus here? I mean, in principle, what we should add here? Yeah, okay, yeah. You add a capacitor charged to that particular voltage. So you take a capacitor, and this has to be charged to Vr plus, and that you keep doing it periodically so that the capacitor sustains the voltage. Okay. And let us say you do this in one clock phase, I don't know, say clock phase by 1, doesn't matter. In the other clock phase, you go and connect the input. So this voltage will be the required voltage. Fine. So, but one minor thing to note here. Let me write it big. Vr plus. So as of now, if I feed this signal, the signal going to the gate is Vi plus minus Vr plus, and remember, Vi plus was some common mode plus the differential input by 2. Similarly, Vr plus is the common mode minus the differential reference by 2. If I take the difference, I get Vid by 2 minus some Vrd by 2. Correct? And this voltage, if I feed this directly, do you think the transistor will be fine? No. This is just a small signal thing you want. So to this, once again, you need to add a common mode, VCM. So which means here also I should add the VCM here. Okay. So which means I can simplify this. This is Vi plus. Fine. Okay. I mean, this extra VCM is coming because I want to make sure I am adding a proper bias before feeding it to the transistor. So that makes, I mean, that means the signal that goes to the gate must look like this. Is that okay? I mean, the idea is we had bias voltages in both of them. When you directly subtracted, the bias voltage got cancelled. So what I'll do, I'll make sure the bias voltage is in only one of them, in the other it's not there. Right? So the capacitor here should now be charged to which voltage? Vr plus minus VCM. So what will I change here? Minus VCM or plus VCM? Now if I do this, this capacitor is going to get charged to the required voltage VR plus minus VCM. So we get the proper voltages fed to the gate.
Can you explain again why we have added VCM? How it is getting cancelled after like we had
This, if you didn't do anything, the signal going to the gate is this Vi plus minus VR plus, and that is basically this fellow. It's a small signal differential input minus another differential reference voltage. This obviously can become less than 0, right? I mean, assume that the input is very small. You are comparing with a reference voltage close to VDD. This is going to be negative. So as you can't feed this as such, you have to add a bias voltage. So you add the bias voltage, then I rewrote this.
to make sure that transistor is a non-state.
Yeah. And again, right, remember, whenever we are drawing any ground here, typically when we draw, it is all small signal ground. In the actual circuit, you go and connect it to VCM. That's the simplest thing to remember. Anytime in differential circuits or in generally any circuit you draw grounds, it is all small signal ground. So that node has to be connected to a bias voltage finally.
So this VCM is not VCM.
No, this is bias voltage. Yeah.
If it is like more cancelling VCM in between VI
Hmm.
plus and VR minus, then why we are previously adding VCM?
Okay, that's why, right? This question is then why did I even generate this voltage? Why did I even generate the voltage that added VCM, right? The problem is we don't have negative VDD here. You only have 0 on VDD. If we had negative supplies, yeah, you could do it, but we don't have negative supplies in practice. It is all from 0 to VDD, so the differential reference has to be given like this. Yeah, good question. So cool. So now let's me finish this. So I'll have the how will I write it here? On the other side, I have the same structure. So for the completeness sake, I'll draw this. I'll remove this. This is fine. So if I draw the other side, it's gonna look the same thing. So I have the capacitor. The input minus is done here. So here I'll have VR minus VCM. This will be done in one case. So now in which clock phase I should activate the comparator? Clock phase 2, because in clock phase 1 this is kind of reset to VCM. In clock phase 2 is when you activate it.
So when we do the sampling, we now have 2 clock phases.
Correct.
We need one more clock phase for the sampling.
Yeah, I mean the thing is right now when your clock phase 2 is active, the input is directly given and you can think of it as being sampled across the gate capacitance. I will come to what you're saying just now. Hold your thought. So yeah, as of now, looks like this is fine, but in practice, one issue is there before you actually can deploy this. So any questions on this? This is fine. Cool. So now let us say, yeah, one thing to forgot to say is in the flash ADC, as we saw, if I have n bits, I need 2 power n minus 1 comparators. So if I want to increase the resolution by 1 bit, by how many times the number of comparators increases? It kind of doubles, right? So the complexity kind of exponentially grows. So that's why typically we don't use it for really large resolutions. Probably 4 to 5 bits is the typical, like base values. But the nice thing is it is one of the fastest because in one clock cycle you kind of get the entire thing. So now let us say you are making a 5-bit flash. How many comparators I'll need? 31, 2 power 5 minus 1, okay. So 31 comparators are there. So physically you will place one comparator here, let us say one here, and let's say the 31st comparator is here. Okay. And let us say this is the clock. This clock has to go to all comparators. It will go here, and to the last comparator it goes like this. Let's say the clock that is reaching the comparators I call as C1, C2 and C31. if the clock reaching the first comparator looks like this, how do you think the clock reaching the last comparator will look like? There will obviously be a delay, right? So this is going to be slightly delayed. I'm just exaggerating and drawing this. And remember, we are locally sampling the input across each of the things. So which means the signal that the first comparator sees will not be the same the last one sees. Right? So do you think that will be a problem or not a problem? Why? I mean, this delay is fine. I mean, I'm still operating in one clock cycle. Let's say the delay is small. Typically, it's going to be small, right? We have, let's say, 30 comparators, few tens, hundreds of picoseconds. I mean, if there is a delay, right, what happens actually? If the clock has a delay, the input processed by this fellow and this fellow, will they be same? They'll be different. So if they are different, what do you think can happen? What do you mean by mismatch? Huh? Okay, let me put it this way. So let us say the input is a low frequency signal. If there is a delay in the clocks, do you think the inputs processed by the comparators will be different or roughly will be the same? Input is kind of varying slowly. So if let us say the first comparator samples here, the last one samples here, it's okay. But let us say I am looking at really high frequency signals. So at this point, the signals seen by both the comparators are going to be drastically different. So which means instead of taking decision on this input, some other comparator is taking decision on some other input, that is going to result in an error. Right? For example, let us say the input should have been this. Let us say you are comparing a reference voltage here. This should have been 1. But unfortunately, the last comparator is seeing this and sees the input is smaller than the reference, it might say it's 0. Okay. So this is a problem, and okay, this is called clock skew.
So why are we doing comparison before sampling? Quantization should happen after.
Yeah. So here the think about it. So the way it happens is the input is directly given here, right? And the comparator kind of responds continuously, and the thing stops the moment the regeneration happens. The sampling is not explicitly happening here in a strong arm latch. Okay, it's a fine point. So the thing is, you are feeding the input directly. So again, let us say even if you sample the input, the same thing will happen, right? Let us say you do. No, you same thing, right? You are, let us say you're going to be sampling the input separately and feeding it here. This clock is going to be delayed in each comparator.
It will be held for some amount of time, right?
No, but the input is continuously going here, right?
Like suppose first you are sampling.
Let us say this is the first comparator. Okay, the input. Let us say the clock edge for the first comparator is this. Clock edge for the last comparator is this. When you are sampling once, you will have the same issue. Right? I mean, this is the same signal. The first comparator is, let us say, sampling here. The second comparator might be sampling somewhere here. So there itself you are having this issue.
I was talking like if you are doing sampling and this comparison separately.
That's where I am coming at, right? See.
Sampled it.
Yeah, that's where I am coming at now. So now the issue is because we are doing this locally in each comparator. So as he is suggesting, instead of kind of sampling it locally, you make sure the signal is first sampled, and the sample signal is kind of given to all the comparators, right? In that case, the signal going to all the comparators will be held like this. So which means it doesn't matter if the first comparator samples here, second comparator samples here. No, that's what you are saying, right? Yeah, that's what you do in practice. So what we need to do is the following. We need to have global sample and hold. And once I sample it, remember I can't feed this directly to the comparator because the capacitor will lose some charge. So we have to buffer it. And one thing about this is, again, as we saw, flash ADC, we use it for, let us say, max 5 bits or something. What is the maximum SNR for 5 bits? About 30-31 dB. For 30-31 dB of linearity, you don't need to use switch capacitor amplifier and all that stuff. Even a simple single transistor voltage buffer will work. So that's what we do. And this is buffered, and then this is going to go to all the comparators. Okay. And remember this, let us say strong arm latch. The output of the strong arm latch has to be given to another SR latch so that it is held for the whole clock period. And then you add up all the thermometric bits, that will give the n bit binary. Okay. So this is what we do in practice. We have a global sample and hold so that after sampling you give the held signal to all the comparators, so that even if there is a skew in the clocks, the signal finally seen by all the comparators will be same.
So sir, all these strong arm latches will be active during 5 hours.
Yeah, we'll look at the clock phase maybe. So let me draw this. So this is the So let us say this is the way in which we are subtracting the reference and feeding into the comparator. So now what I am saying is I am feeding the input in clock phase phi 2. If the input here is given in clock phase phi 2, which means the signal is held in clock phase phi 2. So in which phase this sample and hold should sample the input? In clock phase phi 2, the signal is held. So this, remember, this is a simple track and hold, right? If let us say I call this phi, when phi is high, it is going to track the input. Phi is low is when we are going to hold it. And this fellow should be taking the input during this phase. So in which phase I should be sampling? Phi 1. So in one clock phase phi 1 you sample, in clock phase phi 2 it is completely held, and that held input is what is given. So this is essentially one way in which you can subtract the reference. You can also do a slightly different way. See, here what we are doing is we are actually storing the reference VR plus minus VCM in the capacitor, feeding the input. So here you get input minus the reference, right? But you can do the other way also. You can actually sample the input separately here and store the input, feed the reference. So reference minus input goes. A minus B minus A is just a sign difference. So that is something you can do. So which means I'll first sample the input in one clock phase and store it across the capacitor. So the capacitor is charged to this. Then I connect the reference here and then I finish the circuit. It won't be there, right? Because the input that is coming here is again held. Okay, so actually let's actually look at that. Let me not show the clock phases now. Okay, so here you see the input is sampled in clock phase phi 1. It is held in which clock phase? Phi 2. So I should be sampling the input here during which clock phase? Do I want to sample the signal which is changing, or the sample the signal which is held? I want to process the held signal. Signal is held in which clock phase here? Phi 2. So in which clock phase I should be connecting the switches here? Okay. We'll resample it here, but we are resampling the held signal, so it's okay. So which means I will connect the switch in which clock phase? 1. So when will the comparator be activated?
In 1.
In phi 1. Okay. Because in phi 2 you see this is pull to VCM. Only in phi 1 you are actually feeding the signal. Again, both have their own pros and cons. That will be a problem for you to work out and understand. But I mean, from top level, it can use either of them, right? There are just fine differences. But the idea is the same. You kind of generate the differential references using two resistive ladders, okay, and then store the reference in a capacitor or store the input in a capacitor and feed the other signal so that the signal minus the reference or reference minus the signal is given to the comparator. That's all. Now, there is also one other common way in which this reference subtraction is done. So for that, let's look at the strong arm latch once again. So let me just draw a portion of the strong arm latch. Or yeah, this is how it's going to look like. Here I have cross coupled NMOS. And then I have cross coupled PMOS. I am not drawing that. So what I want is, I want to compare this, right? Vi plus minus VRK plus minus Vi minus the kth reference, like this. This is what I want to do. Of course, plus VCM, that I am not drawing. Okay, bias is all there. Don't worry about it. So I can kind of rewrite it like this. It's Vi plus VRK minus, fine, minus both are same. Okay. Now let us say my job was to just compare Vi plus with Vi minus. What will be the signals I feed here? If I just were to compare Vi plus with Vi minus, what will I feed to the inputs of the things? Vi plus and Vi minus. Simple. And recollect from strong arm latch, initially you reset all the nodes here to VDD. When the latch is activated, these fellows are not active. Initially only these transistors are active. So again you have parasitic capacitors here. You will be drawing currents. Okay. Oops. You will be drawing currents from these nodes, and remember the current drawn in this transistor will be proportional to the input Vi plus. So I will just say this is proportional to Vi plus, proportional to Vi minus. Okay. So the point to remember is, if I were to compare two signals, I should be drawing a current proportional to that voltage from this capacitor, draw a current proportional to the other voltage from the other capacitor. That's what should happen. Now let us say I want to just compare VRK plus with VRK minus, or VRK minus with VRK plus. If this is what you are supposed to do, how will you do? Yeah, let us say you have a similar structure, right? The same thing. You just replace the inputs with, let me erase this, hold on. So at one end you feed, let us say VRK minus or plus, whatever. So which means the current you will be drawing here will be proportional to this fellow. Here it is proportional to this fellow. And then you have the same structure here. But now what I want to do is compare this. So which means from this capacitor, the current I draw should be proportional to Vi plus plus VRK minus. Similarly on this side it should be proportional to this voltage. I know how to generate a current proportional to Vi plus and these voltages. So how can I make sure I draw a current from this capacitor that is proportional to this voltage? I have to, basically if I were to compare these two, I need to make sure the current I draw from here should be proportional to Vi plus VRK minus. I just need to add the currents. Adding currents is the simplest thing you can do in a circuit. I'll erase the parasitic capacitor. So you basically connect this. No. Oh yeah. I mean, you are right. I mean, that is in large signal. In small signal, right? Fine. So if I do this now, we are drawing the appropriate currents from this. So this will again do the same, thing as before. So this is another way in which you can subtract the reference. Let's say the third variant. Unlike in the previous two cases, where we subtracted the reference in voltage, we basically stored the voltage in a capacitor to act like a voltage source and subtracted the voltage. Here, how is the reference getting subtracted? In current domain. We are taking the voltage, converting it to a current, and then doing the addition subtraction in current. This is the other way in which you can do. Again, all the three will have their own pros and cons. You can analyze. But yeah, one thing to notice, see, here we are feeding the reference voltage to the gates, right? So and remember, reference voltage is VCM, let us say minus some VRD K by 2, right? So if this reference voltage is really small, then the transistor might not be activated. Okay, so you can use this as long as the reference voltage you have in your circuit, they are all reasonably high, so that the transistors can be turned on.
So the bottom MOSFETs would be operated by same clock.
Yeah, same clock. Yeah, 5C, 5C. Yeah, true. Cool. So now you guys know how to make a flash ADC. So
Why transistor not turning on is an issue?
oh, because here the main thing.
Transistor is not turning on, the complementary one would be on.
Yeah, but the deal is we have to make sure that we are drawing a current proportional to this, right? If this is not ensured, you might have wrong decisions. So bottom line, in practice, a flash ADC will look like this. You have a global sample and hold. Okay, this is that. This is the sample and hold, and then you have a small buffer. This will be a single transistor buffer, and then you subtract the reference with the input, so that you do that using either of the three variants you saw, and then you feed it to the strong arm latch or any latch you have. Store it in another proper latch that will give the thermometer codes. You sum up all of them and get the n bit data. Okay.